Good morning, my dear children. Welcome to the second session. Today, we are going to learn the third concept, that is Theorem 1, 2, and Euclid's division lemma. Theorem 1. Let x is equal to p by q be a rational number where q is of the form 2 power n into 5 power m, then x is a terminating decimal. Example 7 by 40. Denominator of 40 can be written as 2 cubed into 5. So 7 by 40 is a terminating decimal. If you see here, the prime factorization of 40 is 2 cubed into 5. So which is expressed in the form 2 power n into 5 power m. That's why 7 by 40 is a terminating decimal. Then what is theorem 2? Theorem 2 is that x is equal to p by q be a rational number where q is not of the form, q means denominator is not of the form 2 power n into 5 power m, then x is a non-terminating recurring decimal. Let us see one example. 11 by 2. The prime factorization of the denominator 12 can be written as 2 square into 3. Here denominator is not of the form 2 power n into 5 power m, because if you observe here, the prime factorization of 12 is 2 square into 3. Other than 2, 2 and 5, we have, other than 5, we have 3. So it is a non-terminating recurring decimal. Euclid's division lemma. Given positive integers a and b, there exists unique pair of integers q and r satisfying a is equal to bq plus r, where 0 less than or equal to r less than b. Using Euclid's division lemma, find the HCF of 900 and 270. You see here how the Euclid's division lemma is to be applied to find the HCF of the given two numbers. 900. Here the dividend is 900 and divisor is 270. So 900 is equal to 270 into 3. 273 is 810, which is nearer to 900. And if you find the difference of 900 and 810, the difference is 90. So dividend is equal to 900, divisor is equal to 270, quotient is equal to 3, and remainder is equal to 90. Now, the divisor in the first step is going to become the dividend in the second step, whereas the remainder, which is going to become the divisor. So now 90, 270 is equal to 90 into 3 plus 0. That means 93 times is 270, the remainder is 0. So with what divisor you got remainder 0, that is HCF. This model actually you have learned in the lower classes, but this is using Euclid's division lemma, means using the formula you are finding the HCF. So once again, I'm explaining children here. So 900 we can write as 270 into 3, that is 810, which is nearer to 900. So the difference is 90, which is the remainder. Then 270 will become the dividend and 90 will become the divisor. So 93 times are 270, and which gives a remainder there 0. That's why the HCF of here with the divisor 90, we got the remainder 0. That's why HCF of 900 270 is 90. Based on the above concepts, some of the models from exercise 1.1 and 1.2 and 1.3 I'm going to explain now. The first model is check whether 6 power n can end with a digit 0 for any natural number n. 6 power n is equal to 2 into 3 whole power n. That is equal to 2 power n into 3 power n. To get any number ending with 0, it must have the factors as in the form of 2 power n into 5 power n. But prime factors of 6 are 2 and 3. So it doesn't contain 5. Hence we can say that 6 power n can never end with a digit 0. Another model, how will you show that 8 into 13 plus 8 into 13 into 5 is a composite number? Solution, 8 into 13 plus 8 into 13 into 5. In this, 8 and 13 are common. So if you take 8 and 13 common, the leftover in the first part is 1 and leftover in the second part is 5. So 1 plus 5, which gives 6. When you rewrite 8 and 6 into the 5 factorization, 8 is a 2 cube and 6 we can write as 2 into 3. So the above number is expressed as the product of primes, so it is a composite number. Another example in the same model, explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. Solution, 7 into 11 into 13 plus 13. In this again, 13 is common. So if you take 13 common, 7 into 11 into 1 plus 1. That is 13 into 7 into 11 plus 1. 7 into 11, which is 77. So 77 plus 1 is 78. So 13 into 78. Again, we can write the prime factorization of 78 as 13 into 2 into 3. So we have expressed here as 13 into 2 into 3. Now the second one, that is 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. In both again 5 is common. Take 5 common. The leftover in the first part is 7 into 6 into 4 into 3 into 2 into 1 plus 1. Because nothing is left in the second one, so we should write it here 1. Now, when you multiply 7 into 6 into 4 into 3 into 2 into 1, the product is 1008 plus 1. 1008 plus 1 is 1009. So 5 into 1009. So the above number and this number both are expressed as a product of primes. So they are composite numbers. Another model. Use Euclid's division lemma to show that one and only one out of n plus 2 or n plus 4 is divisible by 3 where n is any positive integer. Solution, let a, that means dividend, we will take it as n, and divisor b is equal to 3. So we will write this as n using Euclid's division lemma. We can write this as n is equal to 3q plus r. So where q is the quotient and r is the remainder, and r lies between 0 and 3, r can be equal to 0. Let us suppose that n here n will be 3q or 3q plus 1 or 3q plus 2. So if I suppose if n is equal to 3q, then n is divisible by 3, as you know that q is a multiple of 3. If n is equal to 3q plus 1, then n plus 2, you see, according to the question, n plus 2 is equal to 3q plus 1 plus 2. That is equal to 3q plus 3. That is equal to 3, if you take common, 3 into q plus 1. Again, q plus 1 is a multiple of 3, so it is divisible by 3. Now, suppose if n is equal to 3q plus 2, then according to the question, the third one is n plus 4. That is 3q plus 2 plus 4, which is equal to 3q plus 6. 3 into, we can take 3 common there, so we'll get 3 into q plus 2. Again, q plus 2 is a multiple of 3, so which is divisible by 3. Therefore, one and only one out of n plus 2 or n plus 4 is divisible by 3. Now, another model, use Euclid's division lemma to show that cube of any integer is of the form 9m, 9m plus 1 or 9m plus 8. Solution. Let the positive integers be 3p, 3p plus 1 and 3p plus 2. Here, why I have chosen 3p, 3p plus 1 and 3p plus 2? Because we should take only the factors of 9. The factors of 9 are 1, 3 and 9. So except 1, we should take other two, either 3 or 9. You can take even 9 also. But the calculation part is easy, so I have taken 3. So first we'll take 3p and let us cube this one. 3p whole cube, which is equal to 27 p cube. Now in that, if you take 9 common, we will write it as 9 into 3p cube. Now equate the 3p cube is equal to some other variable m. So finally we got 9m. So we got it which is of the form 9m. Now take the second one, 3p plus 1 whole cube. Here you have to use the identity a plus b whole cube, which is a cube plus 3a square b plus 3ab square plus b cube. So a cube, that is 3p whole cube, 27p cube plus b cube, that is 1 cube, which is 1, and 3a square b, 3 into 9p square into 1, that is 27p square plus 9p, 3 into 3p into 1, that is 9p. Now, in first three terms, if you observe here, you can take 9 common in first three terms. So if you take 9 common in first three terms, 9 into 3p cube plus 3p square plus p, then left over is plus 1, you write it separately. Now, let us equate 3p cube plus 3p square plus p is equal to one variable m. Then finally, we'll get it 9m plus 1. Now, the second one which we have chosen, the positive integer, is 3p plus 2. Now, cube this 3p plus 2. That is, again, using that identity a plus b whole cube, we have to expand it. That is a cube, that is 3p whole cube, plus 3 into 3p whole square into 2, plus 3 into 3p into 2 square, plus the last one is 2 whole cube. So 3p whole cube is 27p cube plus 3 into 3p square into 2. The product is 54p square, and 3 into 3p into 2 square is 4. The product is 36p. The last 2 cube is 8. Again, when you observe here, in the first three terms, if you take 9 common, 9 into 3p cube plus 6p square plus 4p in brackets, the leftover, the last term is plus 8, you write separately. Now, let us equate once again 3p cube plus 6p square plus 4p is equal to one variable m. Then finally we'll get it 9m plus 8. So the cube of any integers, we can say that is of the form 9m or 9m plus 1 or 9m plus 8. Thank you, my dear children. I hope you might have understood the concept that what you have learned today, and the sums which are based on the concepts what you have learned, and some more sums which are given in textbook exercise also I have included. So please, once again, you practice all these sums, and you can do some other sums which are left over in the exercise. Thank you, one and all.